Assalamu alaikum. We are team AetherMind from Department of Computing, Shifa Tamir Millet University, Islamabad. We have chosen the category of agriculture for our project. To help farmers, we have built an AI-powered app that addresses all the three problems defined on the web portal. Let me introduce my amazing team. Our team lead is Shiza Amir. Then we have Hamna Noman and myself, Zafar Rahman. Now let's talk about what each of us worked on. Shiza Amir developed the crop yield forecasting module for wheat, which helps farmers predict their expected yield in advance. I, Zafar Rahman, built an AI powered Urdu assistant bot for farmers, which functions as a weather linked irrigation alert system. It chats with farmers in Urdu, recommend the best time to water their fields and inform them about upcoming weather or rainfall conditions. Hamna Numan worked on the crop disease detection module, which identifies crop diseases through image based analysis. Together, our app empowers farmers with smart tools, solution for better productivity. Now, I would like to hand it over to Hamna Numan to tell you more about her part.
This first problem we are solving in our Techathon challenge is crop disease detection, a crucial step towards building an intelligent agriculture solution that can help farmers quickly identify plant diseases and take preventive actions. On clicking the option crop disease detection, the user interface is open. User simply upload or capture an image of a leaf, and the app instantly predicts the type of disease and its confidence level. This makes the solution accessible, user friendly, and highly practical for farmers and agricultural experts. So, the model we are using is EfficientNet B3. Our model is based on EfficientNet B3, a highly optimized deep learning architecture known for achieving state of art accuracy with fewer parameters and faster computations. It is ideal for real time mobile applications, web applications, especially in agriculture, where image classification needs to be accurate and efficient. The efficient NetB3 architecture contains approximately 12 million parameters. These parameters are optimized during training using Adam Optimizer and a categorical cross-entropy loss function. Batch normalization and dropout layers help maintain stability and prevent overfitting. We trained the model using PlantVillage dataset, which which contains thousands of labeled images of both healthy and diseased plant leaves. Before training, the dataset was split into training and validation and test sets, ensuring the model learns, validates, and is finally evaluated on unseen data. We also applied data augmentation, including rotation, flipping, and zooming to make the model robust against variations in lighting and leaf positioning. During training, the model learns to identify disease features from images. We monitor two key matrices: training accuracy and validation accuracy. Training accuracy shows how well the model performs on data it has already seen, while validation accuracy shows how well it generalizes to new data. We also track the loss values, which measures how far predictions are from the correct answers. Throughout training, if validation accuracy stops improving, techniques like learning rate adjustment and early stopping are used to prevent overfitting. After multiple epochs of fine tuning, our model achieved an impressive training of about 99.6 and validation accuracy close to 99.5%. On the complete unseen test data, the accuracy remained consistent, 99.6, demonstrating excellent generalization and stability. The high values confirm that our efficient net B3 model is both precise and reliable in detecting crop diseases. To better understand our model's learning progress, we visualize the training and validation accuracy and loss graphs. As the epochs increased, the training accuracy curve steadily rose, toward 99%, while the validation accuracy followed closely, showing that the model was learning effectively without overfitting. The loss graph, on the other hand, showed a consistent downward trend, meaning the model's prediction errors decrease over time. The closeness of both training and validation curves indicates excellent model generalization and stability, which confirms that our efficient Net B3 model was trained successfully and is performing reliably on unseen data. So, the sub-problem of the stackathon addresses a real and pressing challenge in agricultural crop disease causing significant yield losses every year, especially in regions where farmers lack access to expert guidance. Manual inspection is time consuming, subjective, and often inaccurate. By integrating AI based crop disease directly on into a mobile or web application, we provide farmers and agriculture workers with a fast, reliable, and accessible tool for early diagnosis. Early disease detections allow timely treatment, reduces chemical use, and improves overall crop health and productivity. This project, the sub problem, bridges the gap between technology and sustainable farming, empowering communities through intelligent data driven solutions.
Let's talk about weather and irrigation assistant. When a user opens the weatherbot interface, they see a simple Urdu chat screen just like WhatsApp. The bot greets them with a friendly message and invites them to start the conversation by typing their city name like Lahore or Islamabad. The interface is designed to feel natural and conversational so user can simply chat in Urdu without needing any commands or menus. Once the user sends a message, that text is sent to the backend through an API call. Behind the scenes, this request is handled by our Flask application, where the app.py file acts as the main controller. Inside it, the weather chat endpoint receives the user message and passes it to the process Urdu query function. Inside the weatherbot.py module, that's where all the logic happens. The bot then analyzes the message step by step, first detecting the city name, then identifying which crop the user has planted, extracting the field areas in canals, acres, or marlas, and finally asking how many hours of water they currently give daily. Once the user provides these details, the bot connects to the Open Weather Map API to fetch live weather data, including temperature, humidity, and rainfall forecast for that city. Using this data, the code calculates whether the current season is summer or winter, checks if rain is expected today or tomorrow, and matches it with the crop's water requirement stored inside the bot's dataset. Based on all these factors, it calculates the ideal irrigation time and responds in Urdu with a personalized recommendation. For example, telling the user whether to water more, less, or skip watering because rain is coming. In short, the user experiences a simple chat interface while in the backend, the system combines intelligent text processing, live weather API integration, and irrigation logic, all working together to guide farmers with accurate and easy to understand advice in their own language. Now, Shiza Amin will talk about her role in the project. She developed the crop yield forecasting model for wheat.
Now we will be moving forward to our third task, which is crop yield forecasting. Every year, farmers struggle with unpredictable weather, fluctuating rainfall, and changing soil conditions, leading to uncertainty in harvest outcomes. Our project addresses this challenge by using machine learning models trained on global dataset to predict wheat yield based on real-time climate and environmental factors such as temperature, rainfall, and pesticide usage. This empowers farmers to make informed decisions and optimize their production before the harvest season. Now, moving forward to the front end or the user interface for this, in it we have to the user has to enter four parameters. Firstly, the year for which the prediction is to be made, the average rainfall in millimeter for that year, pesticide use per tons, and average temperature. On clicking predict yield, the system instantly calculates the estimated wheat yield per hectare displayed both in Hg per HA and kg per HA. This simple interface ensures that even farmers with minimal technical knowledge can easily access advanced AI insights. Now let's look at the back end of our model. We use a dataset containing historical global agricultural data filtered only for wheat crops. The model uses numeric features like rainfall, temperature, pesticides, and year to predict yield, trained using random forest regressor within a machine learning pipeline. So the training process includes pre-processing, data preprocessing and normalization, hyperparameter tuning using grid search CV, model evaluation on test dataset, and finally saving the model as a .joblib file for real-time predictions in the web app. The regression model achieved extremely strong performance with the following metrics: 1964.61 mean absolute error, 3812.53 root mean squared error, R square score 0.958, average yield 29,465 Hg per HA, error percentage only 6.67%, which means over 93% accuracy in yield prediction. The system successfully meets the competition criteria for yield prediction error less than equal to 10%, proving its reliability for real-world deployment. Our trained model and clean interface together make Kisan AI Advisor a practical data-driven tool to help farmers plan better crop strategies and minimize climate-related losses. At the commercialization stage, Kisan AI Advisor will evolve into a complete mobile-based AI service offering crop disease diagnosis, irrigation scheduling, and market intelligence. For Pakistan smallholder farmers, this means turning complex AI technology into an affordable digital companion that ensures better yields and improved livelihoods. We used a dataset containing historical global agricultural data filtered only for wheat crops. The model uses numeric features like rainfall, temperature, pesticides, and year to predict yield, trained using random forest regressor within a machine learning pipeline. The training process includes data preprocessing and normalization, a hyperparameter tuning using grid search CV, model evaluation on test data, and finally saving the trained model as a .joblib file for real-time predictions in the web app. The, the regression model achieved extremely strong performance with the following metrics: 1964.61 mean absolute error, 3812.53 root mean squared error, 0.958 R square score. Average yield, the test yield was 29,465 Hg per HA, for which the error percentage only 6.67%, which means over 93% accuracy in yield predictions. The system successfully meets the competition's criteria for yield prediction error less than equal to 10%, proving its reliability for real-world employment. Our trained model and clean interface together make Kisan AI Advisor a practical data-driven tool to help farmers plan better crop strategies and minimize climate-related losses. At the commercialization stage, Kisan AI Advisor will evolve into a complete mobile-based AI service offering crop disease diagnosis, irrigation scheduling, and market intelligence. For Pakistan's smallholder farmers, this means turning complex AI technology into an affordable digital companion that ensures better yields and improved livelihoods. Thank you.